Let's start with example. I have a hypothesis that says minority students are underrepresented in higher education compared to white students, compared to Caucasian students. And this is relative to the proportion in the entire population. Let's pretend that the general population in a particular state in the USA has 30% minority and 70% white people. That's a population proportion. Suppose we go to a particular state, any random state in the United States, there are 30% non-white minorities and 70% white people. And we're going to compare the students, the college population. In the college population, higher education, are minorities underrepresented? Are the minorities significantly less than 30%? Suppose I have a sample of 50 students from a particular university. And I found 10 of them were minorities, 40 of them were Caucasians. 10 versus 40 out of 50. And is my hypothesis supported by the data? Does the data support my hypothesis? First, let's look at what are the hypotheses we are trying to test. We have a research hypothesis, which is also called alternative hypothesis. And this hypothesis says minority students are underrepresented. Minority students are underrepresented. And then the no hypothesis says minority students are not underrepresented. These are the two hypotheses. We are trying to reject the no hypothesis. Once we reject the no hypothesis, we can support the research hypothesis or alternative hypothesis. Lay out the data. So you have minority students versus Caucasian students. This is what you observe. Out of 50 people, you have 10 people who are non-white, minorities. And you have 40 people who are white, not minorities, Caucasians. And do you think this data really shows us support of the idea that we have too few minority students? The minority students are not well represented on campus. Would that be good evidence? So a rough, quick and dirty look would be, look at the proportion. Look at the proportion of these 50 people. You studied 50 out of 50, 10 are minorities, 10 out of 50, that is 20%. 20% of your observation is consisting of minorities. In a particular state, you have 30% non-white or minorities. That's more than your campus proportion of non-white minorities. But is your observation strong enough to support the hypothesis that minority students on campus are not well represented? We don't know. We have to calculate. We have to calculate the probability. And you need a comparison. You need a comparison standard or benchmark. Your comparison is called the expected value. What do we mean by expected? This means that suppose if the null hypothesis is true, suppose the minority students are not underrepresented. Their percentage is just 30%, the same as the general population. What would you expect? How many students would you expect? If we suppose minority students are not underrepresented, they just have the same proportion of the general population. And then out of your 50 students, 30% will be minorities, would be non-white. Third, that's 15. You would be expecting 15 students out of a sample of 50 who are non-white. What is your expected value of the white students? Again, supposing that your white students on campus has the same proportion of the general population, 70%. Out of your 50, of your sample 50 students, you would be expecting 70%. That is 35 of them should be white. This is the expected value. And you are going to compare your observed value against the expected value. This is how you calculate the chi-square. Chi-square, the observed value minus the expected value. We call this a deviation. How far away is your observation deviate or differ from the expected value? For the minority, the observed value is 10. 10 people out of 50 are minority, but you are expecting 15. Suppose there's no discrimination, there's no imbalance. Suppose the minority students on campus would have the same proportion as in the community, in the general population, you would be expecting 15 people on campus out of a sample 50. But you only got 10, and you calculate the difference, the deviation, and you square it. Remember, why do we have to square the deviation? You want to square the deviation score to get rid of all the negative signs. And you divide it by the expected value. So you divide by the expected value to get the proportion. This is proportional deviation. And you do the same thing for the Caucasian students. Observed value is 40. You observe 40 people in your sample of 50. These people are white. What are you expecting? You are expecting 35. You are expecting 35 students out of sample 50 who are white. And now you square it. See here, you get rid of the negative sign by squaring it. And then you divide it by the expected value. So here, you get the results. You don't have negative scores. You only have a positive scores. After you take the square deviation, and you get the chi-square value. Chi-square value, the bigger the chi-square value, the more likely that you will be able to reject the null hypothesis. You want a bigger chi-square values. How big? So we need to go get the critical value or cutoff value. The critical value, chi-square is based on degrees freedom. Degrees of freedom. And here the degrees freedom is a number of groups minus 1. here we have two categories of people, minorities and Caucasians. The degree freedom is 2 minus 1. So that's a degree, how many degrees freedom you have. And the cutoff is given in the chi-square table. Let's look at the chi-square table. In the test, you are going to be given a chi-square table. Chi-square critical values, that's a chi-square. So the chi-square, you're interested in this tail, the probability. You want the chi-square to be large. Larger chi-squares in the shaded area would allow you to reject the null hypothesis. This probability is the probability that you would observe the chi-square value if the null hypothesis were true. If the null hypothesis were true, what is the probability that you would observe this kind of a chi-square value? Chi-square value is based on degree freedom. Degree freedom. Well, in the last example, the degree freedom is one degree freedom, and we want to use a p-value 0.05. In other words, we want to reject the null hypothesis. We would like to reject the null hypothesis. If the probability of observing the chi-square value is less than 5%, we want this area, probability, shaded area, to be less than 5%. And what kind of a chi-square value would be in this region? We have a chi-square value calculated 2.38. 2.38 is 2.38 in the shaded area. Is this 2.38 extreme enough to be in the shaded area so we can reject the null hypothesis? Yeah, that's a question. So we need the cutoff here. We need, yeah, make sure my sound is good. Yeah, make sure that you want this cutoff. What kind of critical value would you have to reach to be included in the shaded area? We look at the cutoff chi-square, 1 degree freedom, 1, and we are looking at 0.05, 0.05. That's the critical value is 3.84, 3.84. 3.84, that is a cutoff value. We need to have a chi-square that is at least 3.84 to reject the null hypothesis, to say that, okay, we have evidence to show that the Caucasian students and the minority students are not fully represented and do not have the same proportion as in the general population. It's less than 30%. That is what we are trying to show. So we get the cutoff point and we look at here. Do we have a large enough chi-square to reject null hypothesis? We do not. Our chi-square value is 2.38 and we need at least a 3.84. In this case, we do not reject the null hypothesis. Our evidence is not strong enough. So the result is not statistically significant. This kind of a chi-square task is called a chi-square task for goodness fit, goodness of fit. Goodness of fit task for your observed value. For your observed value, does your observed value fit a particular pattern? How good is a fit? Your observed value is 10 out of 50 students, 10 of them are non-white minorities. 40 of them are white majorities. Does this pattern feed the 30% minority pattern? Does this pattern feed the pattern of 30% minorities or 70% Caucasians? Well, your research hypothesis is no, it does not feed. The 10 out of 50 minority finding is too few. There are too few minority students to fit the pattern of 30-70 deviation. And your null hypothesis is that yes, it's a good fit. It fits the pattern. So you are trying to reject the null hypothesis. And you show the chi-square value. The chi-square value in this case is not extreme enough, not large enough to reject the null hypothesis. We cannot say that with this evidence, we show minority students are underrepresented, does not fit the pattern of 30% versus 70%. This is a chi-square test of goodness fit. How good is a fit? Another kind of a chi-square test is a test for independence. Chi-square test of independence. To test independence, you are testing two variables. You are trying to say two variables are different from, independent from each other. Look at the example, advertising on cultural values. You have a market researcher wants to know whether American TV commercials express different cultural values from Asian TV commercials. They have collected 5 American and 5 Asian TV commercials. They coded the theme of each TV commercial to the cultural values it is expressed. They had 3 categories. So they had 3 categories of social values. One, American values such as individualism, competitiveness, etc. And also Asian values such as collectivism, etc. And universal values. Universal values would be values all people would like. Beauty and health, these are universal values. They expect to find that the 3 types of values would be distributed differently between American commercials and Asian commercials. In other words, what they are trying to show is that American TV commercials would have a more individualistic values and competitive values than the Asian commercials. The Asian commercials would have a more collectivism values than American commercials. This is what they are trying to show. Look at the data. You have these TV commercials, and you call them. You have American origin, Asian origin. So here, 1, 2, 3, the first 5 commercials would be all American commercials. From these are kind of recorded from television in the United States, American TV stations. And then the next 5 commercials all have Asian origins. They are recorded from TV programs from Asia. two categories, American versus Asian. For each TV commercial, you code what kind of value is it expressing? Is it showing something about individualism, or is it showing something about family, groups, collectivism, that kind of values, or is it universal, health and beauty? For this successful case number one, for commercial number one, it came from USA, it came from the United States, and it shows American value. It shows individualism, winning, competing, etc. For the second American commercial, you have the same value, American. And for commercial number three, it comes from the United States and shows the American value. But look at number four, case number four. This is a number four, a commercial number four. It comes from the United States, but shows a universal value. That is like health and beauty. Also for number five, from America, shows universal value. And then you code the Asian commercial, the next five. Number six, come from Asia, Asian origin, and shows collectivism, Asian value. Number seven, same thing. But look at number nine. It comes from Asian country, but shows a universal value, health and beauty. Also number 10. So these are the distributions. You have these distributions of commercials from different regions, and also the values they are expressing. How do we lay out the hypothesis? The research hypothesis says Asian and American commercials express different values, different proportions of Asian and American and universal values. The proportion of values would differ between Asian and American commercials. That's a research hypothesis. In other words, the proportion of values would be dependent on the origin. The proportion of individualistic versus collectivistic versus universal values would be depending on where the commercials come from. If it comes from America, it would have a higher proportion of American values, individualism. That's a research hypothesis. The null hypothesis says American and Asian commercials would express the same proportion of different values. The proportion of Asian, American, and universal values will be the same, but not differ between the two categories, between the two origins, USA versus Asian countries. These are the two hypotheses. What do you want to do with your data? You want to use your data to show that the null hypothesis is not very good. You want to show that if the null hypothesis were true, you have a low probability of observing your statistics, observing this pattern of numbers. You want to reject the null hypothesis. The question is that what kind of statistics would you need to compute to test the null hypothesis? In this case, you would compute a chi-square. You would compute a chi-square for independence. And look at the chi-square calculation. For any chi-square calculation, you are comparing observed value with expected value. Observed value, let's see here. You need this 2x2 contingency table. When you're testing the contingency or the dependence between two variables, you need to build the contingency table. Here, this is frequency table. American commercial expressing American values. American commercial expressing Asian values, expressing universal values. Asian commercials expressing American values, Asian values, universal values. And you need to find the observed value, and expected value. Let's look at the observed value. Observed values are outside the parentheses. Observed values are given. You have a total of five American commercials. Out of 5 American commercials, how many of them expressed American values? You go count. So these 5 are American commercials. How many of them would express American values? 1, 2, 3. These are the 3 expressing American values. How many of them would express Asian values? We don't have any. So it's a 0. How many of them would express universal values? 1, 2. You have 2 expressing universal values. So lay them out. The American commercials, you have total 5. 3 express American values. 0 express Asian values. And 2 express universal values. And then how about Asian commercials? How many of them expressed American values? Out of 5, you don't have any. You don't have any one of them expressing American values. So that's 0. But you have 3 expressing Asian values and 2 universal values. Those are your observed value. For Asian commercials, 0. No, none of them express American values. Asian values, 3. And then universal values, 2. So this way you get all the observed values. This is your observation. And then your expected value. So how would you do the expected value? The expected value, what kind of expected value would you have for American value with American commercials? For American commercials, the 5, you got a total 5. And how many of them would you expect to express American values if there's no relation between the 2 variables, if the 2 variables are independent with each other? That's the expected value. And you have a way to calculate that. Row frequency. Where's the row frequency? Row frequency divided by total. Or row frequency is here. Row frequency is 5. You have 5 American commercials, and you have a total of 10 out of 5. Half of them are American commercials. That's a proportion of American commercials. And your times column frequency. Column frequency here, 3. Altogether, 3 commercials expressed American values. Suppose this is basically dividing the 3 American values between American and Asian commercials. If these two variables don't matter, don't depend on each other, you would be dividing this number, 3 American commercials, according to the proportion of Asian versus American commercials altogether. And in this case, you have equal proportion. 5 American commercials and 5 Asian commercials. This means that you would divide these 3 equally between the 2 categories, between American commercials, 1.5 for American, 1.5 for Asian commercials. This is what you would expect Asian commercials versus American commercials expressing American value. They would be equally likely to do that. This is the expected value for these 2 cells. And you do the same thing for everyone. See here, with Asian values, you got a total of 3. You counted all together, you have 3 commercials expressing Asian values. And suppose if the 2 variables, value and source origin, do not depend on each other, how would you divide the 3 Asian values? You divide it according to the proportion of Asian commercials and American commercials. In this case, they have the same proportion, and they should have get the same division, get the same allocation. Each of them will get 1.5. For the universal values, you do the same thing. You got altogether 4, 1, 2, 3, 4 universal values expressed in the commercials, and you divide them between American versus Asian sources. In this case, you have the same proportion, 2 and 2. This is your contingency table. You have expected values in the parentheses, and you have observed values outside parentheses. Now, you want to compare the expected value with observed value. That would give the chi-square. You would work with all the cells. For the first cell, the observed value is 3, and you get the deviation. 3 minus 1.5. And you divide it by 1.5. That is the expected value. For next cell, 0 is the observed value, but your expected value is 1.5. You were expecting 1.5 American commercials expressing Asian values, but there's none of them. 0 minus 1.5, you square them. Basically, you're getting a squared deviation, SS. You are getting an SS. So I went this way. For the next one, Asian value, 0 minus 1.5 squared divided by 1.5. For the last column, so I went by the columns. Last column, you have 2 cells. 2.2, well, they have the same value. Expected value versus observed value. They have the same, so they don't contribute any deviations. Larger the deviations, the more contribution a cell makes to the total chi-square value. And then these 2 basically cancel each other out. You don't get any deviation. They're zeros. And then you get the chi-square value. And then you want to get the critical value for comparison. Is a 6 large enough? The chi-square of 6 large enough for you to reject the null hypothesis. Again, you need the table. You need to go to the chi-square distribution table to find out. You need to get a critical value. Again, you need to find out whether your chi-square is 6. Is 6 extreme enough to fall in the shaded area to reject the null hypothesis? Is a 6 large enough? So you need to find out what kind of value, what kind of critical value it will take for you to reject the null hypothesis, the cutoff. Again, you need degree freedom. Degree freedom for this contingency tables is number of rows minus number of minus 1 times number of columns minus 1. Here, what rows? How many rows do I have? 2 rows. 1, 2. You don't take the sum. This is not included in the number of rows. In the row data, you have 2 rows. American commercials versus Asian commercials. That's number of rows. You take that minus 1 and times the number of columns minus 1. Number of columns, 1, 2, 3. You have 3 columns. And you don't take the total. Forget about the total. That's a 3 minus 1 degree freedom. And you take the difference and time them. So the degree freedom is 2. Altogether, you have a 2 degrees freedom. Now you look for the cutoff. With 2 degrees freedom, let's use 0.05, 0.05, 2 degrees freedom, 599. And that's close. Cutoff. Chi-square 2 degree freedom at 0.05 level is 5.99. And then you compare your statistic, that is 6, with 5.99. And you find that it's larger than 5.99. You can say we reject the null hypothesis. We believe that the proportion of American values and Asian values in the American versus Asian commercials are not the same. There are some differences in the proportion between the 2 groups on expressing Asian values versus American values. This is chi-square result conclusion. Yes, we do reject null hypothesis. This is called the test of independence, chi-square test of independence. It allows you to test whether 2 variables are independent or dependent on each other. Look at another example. I'm studying the relation between distance from home to work and the transportation people use to go from home to work. Do they drive? Do they ride a bicycle? Or do they walk? Is that dependent on Is that dependent on how far away people live? I believe that whether people walk, bike, or drive would depend on how far away they live from work. I need a sample. So I studied 120 people who live far from home, 120 people who are far from home, and 80 people who live close to work. So I've got altogether 180, 200 people. 120 of them live far away, 80 live close by. And I ask them how they drive, how they get to work every day. Among those people who live far away, 60% drive, 6 drive, 30 walk, and 30 bike. On the other hand, among those who live closer to work, 20 drive, 20 ride a bicycle, and 40 walk. This is the pattern data I got. And we want to make the contingency table. This will be 2 by 3. 2 by 3, out of all the people, you have those people who live far away and those people who live close by. And for those people who live far away, 6 of them drive. 30 of them, 60 drive, 30 ride a bicycle. Another 30 will walk. Altogether, you have 120. Total is 120 people. For people who live close by, 20 would drive, 20 bike, 30 walk. The total of them, those people who live close by is 80. Are they dependent or independent? Are they dependent or independent of each other? In other words, how you go to work, drive, bike, or work, is that dependent on how far away you live from home? That is a question. So we got the expected, or we got the observed value. We know the observed value, but we need to calculate the expected value. The expected value is based on the assumption that the two variables do not dependent. It's based on the assumption that people's ways of transportation would be independent from how far away they live away from home. So basically the expected value is about how you divide the total number of people who drive. You have 80 people, altogether you have 80 people who drive. If there's no, if the how many people drive is independent from how far away they live from their home, and so this proportion is determined by the proportion of far away people and close people. And here is a row frequency divided by n. The row frequency divided by n would give you the proportion of people who live far away versus who live close by. And then the column frequency. Column frequency in this case will be how many people drive, how many people are bicycle users, how many of them walk. And then you divide these numbers according to the proportion of far away people and close by people. And you get the expected value. The expected value for people who live far away and drive. Altogether, you have 80 people who drive, and the proportion of faraway people would be 120 over 200. Of the 200 people, you have 120 who live far away. And then how about those people who live close by and drive? Your expected value would be out of all the people, out of the 80 people who drive, how many of them would be coming from those who live close by? That would be the proportion. Proportion of same as the proportion of people who live by. So you have 80 out of 200 who live close by. These are the what do you expect? This would be what you would expect if the two variables do not depend upon each other. Getting the expected values would give you the deviation, and you calculate the deviation, square deviation. For the first cell, people who live far away but drive, your observed value is 60, and your expected value is only 48, so you get the difference. And you divide it by the proportion, divided by the expected value. Expected value is here. And then for those people who live close by and drive, you have the deviation. Deviation between observation and expected value, square deviation divided by the expected value. You would have to do this for all the cells, for all the different cells. And here I need to complete that. I didn't complete this one. So here's so for this one, bicycle. People who live far away and who ride a bicycle. The expected value is 30, observed value is also 30, and you divide by 30. You divide by the expected value, but it's the same as the observed value. For this cell, people who live close by and ride a bicycle, you divide by the expected value. For the workers, those people who live far away and walk, 30. But you are expecting 42. You are expecting 42. And you divide by the expected value. For this one, last cell, these are the workers who live close by. You observe 40 people who are kind of walking among those people who live close by, but your expected value is only 28. And then once you do the calculation, you can get the chi-square. You get the chi-square and you compare it against the cutoff. Cutoff, here you have degree freedom. Number of rows, -1, you got 2 rows, close versus far away. Number of columns, 3. You have a bike, drive, and walk. And the total degree freedom is 2. So let's see, we figured this out before. 2 degree freedom would have a cutoff point of what? 2 degree freedom at 0.05 level of significance would have a cutoff of 5.99. 5.99 is a cutoff. With 2-degree freedom at 0.05 level is 5.99. Once you calculate your chi-square value, you can compare it with a 5.99 to figure out whether it's extreme enough to reject the null hypothesis. Dependence. Yeah, there's a subtle difference between chi-square test for independence and chi-square test for homogeneity. So we're going to talk about the difference when we go through the exams, go through the quizzes. Let's do a quiz. See if we can do a quiz 29. Let's see, a quiz 29. Let's see, quiz 29. Let's do quiz 29. To test a claim, the dog bites more or less depending on the phase of the moon. A university hospital counts admission for dog bites and classifies added moon phases. Classified. Yeah. So basically, dog bites admissions at the hospital. New moon, first quarter, full moon, last quarter. And you would get, say, this is the observed value. 23 for new moon quarter, first quarter, 27. Full moon, when the full moon is coming, 47 dog bites. And then 38 for the last quarter. The expected number are all 1 in 4. Basically, you are dividing the full months into 4 portions. New moon would be 1/4, 1/4 of the time. First quarter is 1/4. So basically, each segment, each period would have 1/4 of the time period, the whole month, whole moon cycle. Altogether, if you add up all the dog bites and divided by 4, you would have a 36. For all the quarters, you would be expecting 36 bites. And you want to know which 2 categories contribute to the largest component of the chi-square test. 4 quarters, which 2 are the really kind of the most significant contributor? See if I have it here. No, I don't have this question here. The expected value, basically you're looking for the largest deviation from the expected value. How far away is a new moon different from the expected value? 32 minus 36. That's 4, -4. Not a big difference. And then you look at last quarter, observed value 38, but the expectation is 36. The difference is 2. Still not really large, not a big difference. These 2 quarters in the middle seems to be really deviant from the expected value. For the first quarter, you are expecting 36. 36 is expected, but you get 27. The hospital only get 27 admissions. So 27 minus 36. Let me get the calculator. 27 minus 36, 9. Difference 9, -9. And then for this guy, full moon, 47. 47 minus 36. So the difference 11. 11. So these 2 quarters have the biggest deviation from the expected value. They differ from the expected value. They have a really poor fit with the expected value. They don't fit the expected value really well. This would be the most significant contributors of the chi-square value. First quarter and full moon. First quarter and full moon have the biggest contribution to the total chi-square. Look at question 2. A random sample of 100 former student athletes. So you have one sample, 100 former student athletes, are picked from each colleges that are members Big East Conference. You have one sample from each college. So how many samples do you have? We don't know. We don't know how many samples you have, but you have independent samples. Students are surveyed about whether or not they feel they received a quality education while participating in university athletics. That's what you are measuring. Which of the following is the most appropriate test to determine whether there is a difference among these schools to the student athlete perception of having received a quality education? This is a subtle point. This is a test about homogeneity. Sometimes it's difficult to kind of differentiate what's the difference between task of independence versus task of homogeneity. And the difference is that the number of samples. In this case, you have a different samples. You have a separate samples. You have many samples. Each sample would have 100 people. Each sample would be coming from one university. And you are trying to test, are these different samples homogeneous? Homogeneous means the same, share the same characteristic. You're testing, are these different samples share the same characteristic or not? Are they homogeneous? Are they very similar to each other? This would be a test of homogeneity. When you have a different samples, you test for homogeneity between among the different samples. But when you have one sample and ask them 2 questions, suppose you have one random sample of athletes, and you ask each athlete 2 questions. Number 1, Where are you from? Which school do you come from? That is one variable. School affiliation. Another question you ask me that, are you getting a quality education? Are you satisfied with the education you are getting? And then this would be a test for independence. You're testing, does the perception of education quality depend on which university they come from? This would be a test for independence. This is because you get this one sample of people, one sample of students, and you categorize where they are coming from. This is a very subtle difference. Look at number 3. A disc jockey wants to determine whether middle school students, high school students have a similar musical taste. Do they have a similar musical preferences? Independent random samples are taken from each group. So here you have multiple samples, independent samples. Each person is asked whether he or she prefers hip hop, pop, or alternative. A chi-square test of homogeneity. So you are testing homogeneity, not independence, because you have independent samples. And you're testing the homogeneity of proportion of preferences, pop, hip hop, etc. The resulting p-value is below 0.05. This means you would get a chi-square value, and you compare it against the critical value for 0.05. It turns out the result is significant. The proportion is less than 0.05. Which of the following is a proper conclusion? What is a conclusion you can make? The p-value is below 0.05. So it is a significant. Look at the number 1. There is sufficient evidence that for all 3 music categories, for all the 3 categories, hip hop, pop, and alternative, the proportion of middle school students who prefer each choice is equal to the corresponding proportion of high school students. It is equal. And you ask, is this a conclusion we can draw? Is this a proper conclusion? And we want to know, is this a research hypothesis or the null hypothesis? No difference. So this hypothesis is saying that of all the categories, high school students and college students would have no difference, would have the same proportion. That's a null hypothesis. And in this case, what do we do with the null hypothesis? The p-value is below 0.05. This means we are rejecting the null hypothesis. We say the null hypothesis does not get any support. So we do not choose this one. This is null hypothesis. We are rejecting it. Look at B. There is sufficient evidence the proportion of middle school students who prefer hip hop is different from the proportion of high school students who prefer hip hop. Is that we're going to show? Can we draw this conclusion? This is focused on hip hop. Do we know that for this particular category, there's more there's different proportion between high school versus college students? No, we don't know. We don't know the research hypothesis. This is not the research hypothesis. The research hypothesis will say there's a difference. There's a difference between high school and college students in preference for any of the categories. We don't know where the difference is located. We don't know it's located in hip hop. Maybe it's not in hip hop. Maybe it's in pop or alternative. Hip hop is not what we're testing. We don't choose this one. Let me go get a glass of water. I'll be right back in a couple minutes. All right. Yeah. So B is not a good answer. B is just too specific. We don't have those kind of specific information. How about C? There is sufficient evidence for all three musical choices. All three musical choices. The proportion of middle school students who prefer each choice is different from the corresponding proportion of high school students. Is this good? No. No. Basically, what we are looking for is a research hypothesis. The research hypothesis is not so extreme. This is not what we are testing. We're testing, is there any difference? Is there any difference in any of the three musical choices? That is the difference between high school versus university students. C is not a proper statement of a research hypothesis. D, there is sufficient evidence that For at least one, yeah, this sounds really promising. At least one of the three musical choices, the proportion of high school students, middle school students and high school students would be equal. So what does that mean? At least one of the three musical choices, the proportion between middle school and high school students will be equal. No, that's not a research hypothesis. We are looking for difference. We are looking for difference in the research hypothesis, not equality. Look at the last one. There is a sufficient evidence that for at least one of the three musical choices, the proportion of middle school students who prefer the choice is different from the corresponding proportion of high school students. Yeah, this is a research hypothesis. This is the one we are supporting. The p-value is below 0.05. We reject the null hypothesis and we support the research hypothesis. And here the E, the last statement, is a proper statement of the research hypothesis. Or we also call the alternative hypothesis. Yeah. This should be the one we are supporting. Yeah, let's talk about, look at number 4. Given a two-way table, it's not obvious whether to perform a task for independence or a task for homogeneity. What is the main difference between the tasks? This is a very subtle question. Given a two-way table, it's not obvious whether to perform a task for dependence or a task for homogeneity. Do you do a task for independence or homogeneity? What is the main difference between the two tasks? How expected counts are calculated? No. Degree freedom? No. The difference is the number of samples. How many samples do you have? If you have one sample, you do a task for independence. But if you have multiple samples, you use a task for homogeneity. With multiple samples, you're testing, are these different samples have the same proportions? Are they homogeneous? Yeah. Oh, that's a calculation question. This computation question. Well, let's look at last chapter, the last piece of information. Maybe today we can take care of all the tests. This part is a small part. Inference for slopes. This is very small part of the test. Why don't we take care of that today? Then we are done with all the content materials, and then we can maybe do a systematic review. So this is a task for slopes, and it's about 2% to 5% of AP exam. This part is all about regression. We talk about a least square regression line. This was at the beginning of the course. We talked about how to calculate correlation and how to calculate regression. Now we want to do a hypothesis test for the slope of the regression line. Let's look at an example. Look at example. Information concerning SAT verbal and SAT math was collected from 15 randomly selected students. You collect the data from 16 students, and you get a linear regression. Linear regression performed on the data using statistical software. And you have here the output. The dependent variable is mass. And then dependent variable mass. So the predictor variable is verbal. Yeah, so you are using the verbal test as a predictor variable, and the dependent variable is mathematics. You have a constant, a verbal, this is predictor variable, and you have these numbers, the t value, the probability value, s squared, r squared. R squared, this is really important. R squared, this is a small r squared. This is the correlation coefficient squared, and you get this r squared. This is important in giving us the proportion of reduction in error. We're going to look at this one a little bit later. We talk about this one at the beginning of the class. Maybe we should look at it more. Here you have the data. This is a scatter plot. Some people have a high verbal scores. These people also have a high math scores. Some people have a lower verbal scores. They also have a lower math scores. Strong positive correlation, strong linear positive correlation. The regression line would be the best fitting line. The regression line would be running through these dots. A regression line has a slope. So if you want to draw the regression line, see if I can draw the regression line here. Yeah. The regression line would be somewhere, it's not precise, but probably good enough. The regression line would have a slope. How steep is the slope? And then it would also have an intercept. The intercept is here. Yeah, it's here. That is when the predictor variable and verbal scores is 0, what would be your predicted math scores? That'd be the intercept. And you get a formula. You need a formula for this line. The formula would be the predicted y equals to a plus b times x. This regression line would allow you to make predictions. Suppose you know that, okay, my SAT verbal score is 550. My verbal score is 550. What is my predicted score on math? My predicted score on math should be here on this line. And you use this formula to make the predicted score on mass. This is the basic logic of regression. So that's regression. And what we want to go? What is a regression equation? What is a regression formula? So regression equation, I shouldn't have got rid of that. Basically, I don't have that anymore. Basically, let me use a Word file here, regression equation. Regression equation. You are looking for predicted y. Predicted y with little hat equals to a plus b times x. And then you need a and b. Where do you go get a and b? In this case, y is mass, predicted mass score. B is verbal score. I mean, X is verbal score. You need A and B. Where do you go get A and B? A is a constant. That's it's constant coefficient. 92.5724. 92. So it's 92.57. What is B? B is a slope. The slope, that is a coefficient for the verbal predictors, 0.763, 0.764. 0.764 verbal score. This line will tell you that as a person's verbal score increased by 1 point, his mass score, predicted mass score, will be increasing by 0.764 points. That's prediction. And this 92.57, what does that mean? 92.7 is here, so that's a one verbal score is 0. When you don't have any verbal score, your predicted mass score is like something like 90, it's around here, 90 point something. That's a regression. That's a regression formula. You write it this way. What is a 95% confidence interval estimate for the slope of the regression? That's 98%. Slope, where's the slope? The slope is here, 0.764. The standard, so here's the standard deviation of the residue. The standard deviation of the residue is 16.69. This is from the computer. So the computer printout tells you that the standard deviation of the residue is 16.69. Standard error of the slope is 0.0556. This is 0.0599. And you have 15 data points. The degree of freedom is 15 minus 2. That is 13. So total degree of freedom is 13. And you have the t value. Yeah. Standard error. Standard error is here for the coefficient. You get this from here. Standard error of the coefficient. Yeah, so the degree of freedom. And then 90, so here, this is critical value, 95%, 95% confidence interval would give you the cutoff t value of 2.16. That's based on the degrees of freedom. 15 data points and minus 2. Why minus 2? Because you have two variables, math versus verbal test. So it's here 0.76, 0.76, that's the slope you calculated. The margin for error, the boundary values, 2.16, that's a t value. 2.16 times the standard error. The standard error, that is estimated standard deviation. Let's look at another example. A random sample of 10 high school students produced the following results for number of hours TV watching per week and GPA. So for this guy, 12 hours for each week or per week. 12 hours per week, GPA 3.1, 21 hours, a lot of TV, 2.3, 8 hours, 3.5. So you have 10 people. You got 10 people on two variables, GPA and TV watching. This person watched no TV at all. His GPA is 3.8, pretty high. And determine the least square length and give the 95% confidence interval to choose slope. Yeah, so now you got let's look at the conditions. Random sample. You have the random sample, that's good. Scatter plot. Yeah, this should be a negative correlation. You can see there's a negative correlation, straight line, linear correlation, and residue plot. You plot all the residues. The residue have no particular pattern. You don't see a curve, you don't see a straight line. It's a random pattern. This would mean the correlation is linear. It's mostly a linear correlation. And you check normal distribution. Normal distribution is normal. And then you go get the formula. Let me get the formula. I'm gonna send you guys a calculator instructions. Calculator instructions. You got to learn how to use a calculator to do this kind of stuff. And I'm gonna use a computer program. I'm gonna use let me use the IBM. Close some of the stuff. Here I go. Okay. 10 students. 10 students give you these numbers. Let me copy this one. So 12, 21, 8. So the first variable is TV. TV watching. No, variable view. TV. And what? Name. TV. Second variable would be GPA. How many hours do you watch TV? 12, 21, 8, 12, 21, 20. 16、16、24。11, 18. GPA. So now I got a GPA. Yeah, 3. Last one. Yeah. All right, so you got the data and we can get the layout. Let's see. We're trying to get the regression formula, right? So how do we get the regression formula? Yeah. Slope. We are trying to get the slope. And we're trying to get the 95 confidence interval for the slope. To get the 95 confidence interval, we need to get the slope first. So I'm going to do a regression, linear regression. Dependent variable would be GPA. TV watching is an independent variable. See what plots can we get? Can we get scatter plots? Normal probability. Let's get this, guys. Normality. Register coefficients. Yeah, this one is the one we are interested. We're interested in this one. Constant is A. B is a slope. So 0.69. See how far we are from them. We might have some numbers wrong. Mm-hmm. 2.6. 16 is 2.6. 16 is 2.6. 2.1. 2.9, 2.6. Yeah, so I got some numbers wrong. Let's do it again. Regression, linear. Yeah, now we get the good numbers. Coefficients, TV, this will be the predictor variable. Predictor variable. Here, we're still trying to get a predicted y equals to a plus b times x. Predicted y will be GPA. So we replace this one's GPA. Predicted GPA. So what's A? From the computer printout. 3.89. 3.89. 3.89. This means that according to my prediction, if somebody watched zero TV, no TV watching, his or her predicted GPA would be 3.89. That's intercept. Where's the slope? Negative 0.072. Negative 0.072. X would be the number of hours a person watch TV per week. And then this negative 0.072 means for every hour increase of TV watching, GPA would go down by 0.072 points. This is relationship between how many hours TV watching and the GPA level times X. Yeah. Now this is a formula, and then we need to get the 95% confidence interval for the slope. The slope is negative 0.072. And 95%, what is a 95% interval? 90% interval would be based on the t-test, the t-value, 95%. Let's go to the t-value, 95. T-distribution, 95, so we want it on both sides, and that would be corresponding to 2.5% on each side, 0.25. 0.25, what degree freedom do we need? 10 minus 2, 10 minus 2, that would be 8. 2.306, so 2.306 plus or minus 2.306. Those are the boundaries, upper and lower boundaries for the interval. And now we need the standard error. So this would be times the standard error. What would be the standard error here? Here's a standard error for the slope. Standard error for the slope for the TV 0.07, 2 zeros, and 0.07. Let's see. So that would be plus or minus 2.306 times 0.007, 0.016, 0.016. That's going to be negative. Slope is negative in this case. In that case, so the slope would be the lower boundary would be plus 0.072, 0.088, 0.088, 8, lower boundary, that's negative. The upper boundary would be negative 0.072 plus 0.016, 0.056. This would be the boundaries for the 95%. Where is that? I don't know. Sorry, here. Yeah. This one is one we're looking at. Yeah, here. A negative 0.887. We're close. Negative 0.88. Right, 88. Okay, this is negative 0.056. 0.55. Yeah, very close. This is how you get the confidence intervals. Look at this one. Distance a caterpillar cross in a random sample 15 periods are plotted. Yeah. All right. 15 seconds. Centimeters distance. 15 time periods. So the seconds, so how far they crawl. 0, 1 second, maybe 3 seconds. The longer time passes, the further away they are crawling. That's a correlation. And here, 95% confidence interval of the slope. Here's the slope. It's the interval for the slope. It's positive. Another measurement of 14 centimeters of 35 seconds is a potential. With the addition of this data point, will the confidence interval change? If so, will the margin of error increase or decrease? 1435. So we got one data point, 14. Where's 14? Here's 14. 14 and 14 centimeters, 35 seconds. 35 seconds here. 14 seconds is right here. And if you draw the line, no, I can't draw the line here, but yeah, the regression line would be really straight up. 1435, 1435. So here, where's the line? 1335. It's close to the line, but not really on the line. Let me copy this one. Get a paint. Yeah, 1345 be here. The regression line will be here. So you are adding one data point. One data point you're adding is here. This is going to be very close to the line. Very close to the line. If you add one more data point, the question is, will the confidence interval change? Will the margin of error increase or decrease? The slope will not change much. The slope will not really not, it's pretty much the same. You will not change the slope of the line. The line is okay. The line would fit this additional data okay. Standard error. So, but if you add one more data point, standard error of the slope will be smaller. So the margin of error will decrease. Yeah. If you compare the two margin errors, before adding the data point, 0.325 lower boundary. And here, after adding the point, it becomes a 3.39. And the range, the interval becomes smaller. Before the data point added, the upper limit was 0.43. After the point, it reduced to 0.415. What would happen if a data point 12 and 1 is added? 12 and 1, 12 centimeters, 1 second, right? 12 and 1. What would happen? 12, where's 12? I'm not seeing where's 12 and 1. So x, oh, x, 12 is on x. 12 is on x. So that'll be 12 and 1. 12 here, 1 centimeter. 12 seconds crawling only for 1 centimeter. 12 is close to the mean of all the x coordinates. The slope of the regression will change little. Patients here, 12 and 1. 12 is very much in the middle on the x. X ranges from 1 to like 24, 23. So 12 is close to the mean. And so the slope will not change. The slope will not change that much. But you might want to move the line a little bit. You want to move the line to take care of this additional point. The slope will not change, but the intercept, this might change. And also with this one, the standard error will change. All right, let's call it a day, guys. Yeah, I'm going to send you guys the video after the class.
Thank you.
Keep reading the book.
Yeah, thank you.
Bye-bye.